All right, let's talk about improvement directions. So first, can we find a way to compute an improvement direction, at least for this kind of ellipse-shaped function, that actually moves us towards the optimum? Well, in fact, we can, using something called Newton's method. Newton's method is a more sophisticated optimization algorithm than gradient descent. Now, we won't actually use Newton's method when we train neural networks, because Newton's method for neural networks is very, very expensive. We can't afford it. It requires too much computation. But you can think of it as a kind of ideal to aspire to. Newton's method doesn't solve all problems. It's not going to solve local optima. It's not going to solve saddle points. But it will give us a much better direction than the direction of steepest descent. So here's the idea behind Newton's method. One of the ways that we can approximate a function, like a function f of x, is by using what's called a Taylor expansion. Many of you probably learned about Taylor expansion in calculus. The idea is that you take some point, x0, and around that point you calculate some derivatives. Maybe you calculate a first derivative and a second derivative. And then you can approximate your function as its value at x0 plus its first derivative times x minus x0 plus its second derivative times 1/2 x minus x0 squared. And then you can calculate third derivatives and fourth derivatives and so on, but we'll just do first and second derivatives. Okay? So if you have first and second derivatives, essentially you approximate your function with a parabola that has the same slope as your function at the point x0 and the same second derivative. Okay? Now, a parabola is not a very good approximation to really complicated functions, but it might be a pretty decent approximation locally in the neighborhood around your point. And of course, you can do the same thing in the multivariate case. If you have a multivariate loss function L theta, you can approximate it as L theta 0 plus the gradient at theta 0 times theta minus theta 0 plus 1/2 theta minus theta 0 transpose times the Hessian times theta minus theta 0, right? So you have a linear term and a quadratic term. In this case, you're approximating your function L theta with a quadratic bowl, a multivariate generalization of a parabola. The nice thing about these quadratic functions is that we can optimize them in closed form. If we want to find the value of theta that minimizes a quadratic function, there's just a closed form expression for it. We don't need any kind of gradient descent for that. So the quadratic approximation, the Taylor expansion, is formed by using the gradient and the Hessian. And remember, the Hessian is just a matrix where every entry is a second derivative. And we can optimize this analytically. So if we want to find the value of theta that minimizes this approximation, we just set the derivative to 0 and we solve. And we get the update theta star is equal to theta 0 minus the inverse of the Hessian times the gradient. Okay? I'm not going to go through the math for this, but if you want to work this out at home, just take the approximation that I've written out here, compute its derivative, set that derivative to 0, and then solve for the resulting value of theta. And you're going to get exactly the thing that I have in the bottom left of the slide. And that will actually give you the improvement direction that will head straight for the optimum insofar as your function is locally well approximated by a quadratic function. And it's probably worth mentioning that the update here in the bottom left looks a lot like gradient descent. So for gradient descent, you would take theta 0 and subtract alpha times the gradient, and here we're taking theta 0 and subtracting the Hessian inverse times the gradient. So we're just transforming our gradient by this inverse Hessian matrix. Okay, so if we could somehow do this, then we would get a really good improvement direction. Now, why is Newton's method not a viable way to improve neural network optimization in practice? Well, let's think about this for a second. Here's our gradient descent update. What's the runtime for one update of gradient descent? Well, let's say that the time needed to calculate each of those partial derivatives is constant. It's not really constant, but let's imagine it was. We have n dimensions in our theta, and we need to calculate a separate partial derivative for each one. So roughly speaking, we would have O of n runtime. The runtime is actually O of n, although in practice we don't calculate each partial derivative separately, we use a procedure called backpropagation, which we'll cover in a subsequent lecture, that ends up calculating the gradient in O of n time. Now, for Newton's method, we need the Hessian. How many entries does the Hessian have? Well, in the same way that the gradient has n dimensions, the Hessian is n by n, which means it has n squared total entries. And our Newton's method update requires computing the inverse of the Hessian multiplied by the gradient. Now, representing the Hessian by itself already requires O of n squared operations. A matrix inverse requires O of n cubed. So at least if we were to do Newton's method naively, it would have runtime that scales cubically with the number of parameters. And if you remember from lecture 1, the number of parameters in a large modern neural network could be in the billions. So something whose runtime is cubic in that would take so long to compute even one update that it would never be viable. Now, an important caveat is that this is only true if we compute the Hessian inverse times the gradient naively. There are fancier methods that can be much faster than O of n cubed because they avoid actually building the entire Hessian. So the trick that you can use if you really want to do Newton's method for neural networks is to come up with an algorithm that calculates the Hessian inverse times the gradient without ever actually building the entire Hessian. And it turns out that there are clever ways of doing that. In fact, they're so clever that with a little bit of approximation, they can actually be linear in the number of parameters. But generally, they end up being very complicated, and they don't tend to be used very much in practice. So because of this, we would really prefer methods that don't require second derivatives, but somehow accelerate regular gradient descent instead, while keeping this nice O of n runtime in the nice simple update form. Okay, so the first tractable acceleration technique we'll discuss is something called momentum. Momentum is exactly what it sounds like. So if we remember this picture from before, gradient descent is going to kind of oscillate back and forth. But if we look at a couple of successive gradient updates, we'll notice that they tend to point in opposite directions. So it's very tempting to think, well, if we can just average them together, if we can just take the average of these update steps, we're going to get exactly the direction we want. So can we modify gradient descent so that we can fix these oscillations by basically averaging together a few gradients? So averaging, in this case, if we were to average together two successive gradient updates, we would get us an update direction that is much better than the one we had from the steepest direction at any single point. So the intuition is that if successive gradient steps point in different directions, we should cancel off the directions that disagree and just keep the directions that agree, and then we'll go in a better direction. So if we see this kind of oscillation business, if we average those out, we'll just get the direction of improvement towards the optimum. On the other hand, if successive gradient steps point in similar directions, we should go faster in that direction. So if we get something like this, where it's roughly going in the same direction, averaging those together would give us a much longer arrow in the right direction. So how can we do this? Well, the update rule we're going to use with momentum is very much like in gradient descent. Theta k plus 1 will be theta minus alpha times gk, where gk now is our improvement direction. Before, it was just the gradient, but now it'll be the gradient plus mu times gk minus 1, where mu is some constant that's less than 1. So we'll basically take the previous direction, multiply it by some decay factor, and then add the new direction. So we'll kind of blend in the previous direction, but we multiply it by, let's say, 0.99. A common choice of mu is 0.9 or 0.99. So what that means is if the previous direction and the new one point in opposite ways, they'll cancel off. If they point in similar directions, they'll actually add together and go even faster in that direction. So in this case, we would cancel off the conflicting parts. And this is a very simple update rule. In practice, momentum actually brings some of the benefit of Newton's method at very, very little cost. There's basically no additional computation that's needed. All you have to do is you have to store the previous GK. So there's a little bit of memory overhead. Now, this kind of momentum method doesn't have very many theoretical guarantees. It's kind of a slightly heuristic improvement to gradient descent, but there's a very closely related idea called Nesterov accelerated gradient. And Nesterov's accelerated gradient, named after Nesterov, does carry very appealing guarantees. In fact, it's provably faster for convex problems than gradient descent, but it's a little bit more complex. So in practice, we usually just use momentum. But if you're interested in optimization theory, then you can look up Nesterov's accelerated gradient. It's theoretically a very, very elegant algorithm, and there's a lot of interesting analysis in convex optimization about Nesterov's accelerated gradient. But since this is a course on deep learning, we're going to focus more on the method that we'd actually use, which is momentum. All right, here's a little demo with momentum. So here I have gradient descent without momentum, and as I increase momentum, one thing you can see is that the solution gets closer to the optimum, so it goes faster and faster along the bottom of that valley, but it also tends to take a little longer to slide to the bottom of the valley. So for a large value of momentum, what you can see is that it kind of has this zigzag pattern, because if you imagine this as a ball rolling around in this landscape, it's going to have some momentum, and it'll roll up the other side before it exhausts that energy and turns around and goes back the other way. But the benefit of momentum is that it does end up getting much closer to the optimum because it slides along the bottom of that valley much more effectively. All right. Now, the next issue I'm going to talk about is the scale of the gradient. So, as we saw before, the steepest descent direction is not really a good direction. So the sign of the gradient is important. It's important whether the gradient points left or right. But how far it goes along each dimension is a lot less informative. So here, at the starting position of the black circle, the gradient in the vertical direction is larger than the gradient in the horizontal direction, but we should actually be going faster horizontally than we're going vertically. So the relative magnitude of the gradient for different directions is not actually that informative for us. But its sign is, because we definitely don't want to be going up at that point, and we definitely don't want to be going left. We need to be going down and to the right, but how much right or how much down, the gradient doesn't really give us very useful information about that. So the intuition is that the sign of the gradient tells us which way to go along each dimension, but the magnitude is not really all that useful. All right, so there's our gradient. Even worse, the overall magnitude of the gradient can change drastically over the course of optimization, which can make learning rates hard to tune. So here's an explanation of this. Let's say that we use the squared error loss if we're doing regression, right? The derivative of the squared error is the difference between f of x and y times df d theta. That's just chain rule. So one of the things we can immediately see from this expression is that the more f differs from y, basically the larger the error is, the larger the gradient will be. And if initially f is very different from y, maybe our initialization is very bad, then your gradients will be huge. And when your gradients are that huge, you'll almost certainly overshoot the optimum and come out the other side. But as your function f gets closer and closer to y, the gradient will become tiny. And at that point, you might be taking really small steps. And then you might want a bigger learning rate. So because the overall length of the gradient depends so much on your function, it can be very difficult to tune your learning rate so that it works reliably for different functions or for different points for the same function. All right. So one idea that could help us mitigate this is to normalize out the magnitude of the gradient along each dimension. Basically, if you can somehow figure out roughly how big the gradient tends to be on average along each dimension and divide by that, then you'll remove these annoying scaling factors. So one algorithm that does this, approximately, is called RMSProp. RMS stands for root mean square. The idea in RMSProp is to estimate the per dimension magnitude of the gradient on average. So for every dimension of the gradient, what we're going to do is we're going to keep track of a kind of a moving average of its square. So we're going to use the scale vector, sk. Sk has the same number of entries as the gradient. And every step, we're going to take the old value of sk minus 1, and we'll multiply it by some factor beta. Beta might be like 0.9 or 0.99. And then we take 1 minus beta and multiply it by the square of every entry in the gradient. So we would expect the vector sk to contain, for every dimension, the average squared value of the gradient for that dimension. So it's roughly how big does the gradient tend to be for that dimension squared. So this is roughly the squared length of each dimension. And then when we update the gradient, when we update theta, we take a step in the direction of the gradient, but we divide it by the square root of sk. So for every dimension in the gradient, we divide it by the square root of the average squared length of that entry. So that means that we roughly divide each entry in the gradient by its average length, which means that if some dimensions of the gradient tend to be very big and some tend to be very small, after this division, they'll be of about equal length. So each dimension is divided by roughly its magnitude. All right. Now, RMSProp tends to do a pretty good job of fixing this scaling factor, but again, it's a somewhat heuristic algorithm. It doesn't have very strong guarantees. A closely related algorithm is called AdaGrad. AdaGrad, you can think of it as basically a more theoretically principled version of RMSProp, in the same way as Nestrov's accelerated gradient is a more principled version of momentum. So in AdaGrad, we also estimate per dimension magnitudes, but we estimate them cumulatively. So we just set sk to be sk minus 1 plus the square of each entry in the gradient. So we essentially just got rid of that beta stuff. And then just like with RMSProp, when we update theta, we just divide each entry in the gradient by the square root of sk. So here's RMSProp by comparison. In RMSProp, we kept a running average. In AdaGrad, we just sum those squared values together. Now, at first you might say, well, that seems like a bad idea because sk is going to keep getting bigger and bigger and bigger. So how does AdaGrad and RMSProp compare? Well, AdaGrad has some very appealing guarantees for convex problems. You can actually prove that AdaGrad will find good solutions efficiently. But for non-convex problems, the fact that the learning rate decreases over time can be a problem. This is an issue, like why does the learning rate decrease? Well, because you keep adding positive numbers to sk, so sk keeps getting bigger, 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 bigger. So that means that you're dividing by bigger and bigger numbers, which means that your updates are smaller and smaller and smaller. So this only works if you find the optimum quickly before sk gets so big that your updates become tiny. This turns out to work in convex problems because intuitively for convex problems, each successive step can be smaller than the previous one because you're always getting closer to the optimum. And because the function is convex, because it curves that way, the slope has to get smaller and smaller and smaller. So you're adding these squared slopes, but the slopes are getting smaller, which means you're adding smaller and smaller numbers. And it actually turns out that for convex problems, the rate at which the slope decreases and the rate at which your learning rate decreases, they actually balance out and you end up reaching the optimum. But for non-convex problems, you might be going down a really, really steep slope, then hit a plateau, and then hit a really steep portion again. And the fact that your sk got so big, and therefore your updates got so small, will really kill you when you're on that plateau. So for non-convex problems, AdaGrad tends to not work so well, and RMSProp tends to work quite a bit better. RMSProp forgets. Over time, the fact that you're multiplying sk minus 1 by beta, and beta is less than 1, means that over time RMSProp will forget big gradients that it's seen a long time ago, whereas AdaGrad will never forget. So RMSProp tends to be much better for deep learning and in general for non-convex problems. Okay, the last algorithm I'm going to discuss, and this is a very commonly used algorithm in deep learning, is called ADAM. The basic idea is that ADAM kind of combines momentum and RMSProp. So in ADAM, we're going to use momentum to accelerate gradient descent, and we're going to divide by a running average of the squared lengths to normalize out the lengths. So here's the ADAM algorithm. It has actually quite a few steps, but the steps are very simple. First, we have what's called a first moment estimate. This is very much like what momentum does. So we take the current gradient, we multiply by 1 minus beta, and we take the previous value of m and we multiply by beta. So it's kind of like momentum. Momentum didn't have the 1 minus beta thing, but very similar idea. So we're kind of accumulating our gradients as we go. So you can think of mk as basically a running average of the gradients. And then we have vk. M stands for mean, v stands for variance. And vk is what's called the second moment estimate. So this is our running average of the squared lengths of the gradient. So it's just like the update for the first moment, only now we're using the squared values of the gradient. So this is a lot like that S vector in RMSProp. And they're both running averages, the first one using beta 1, the second one using beta 2. Now at this point we could just take m divided by the square root of v and we would have an RMSProp style update. But there's a little bit of a problem. Imagine we're just starting off and we set m0 and v0 to be 0 initially. Then m1 will be 1 minus beta times the gradient plus 0. And typically beta 1 and beta 2 are large numbers, like beta 1 might be 0.9 and beta 2 might be 0.999, right? So m1 will be 1 minus, let's say 0.9, so it'll be some small number times the gradient, plus 0.9 times 0. So initially, m will be small and it will gradually build up over every step. And the same for v. And this is a little bit annoying because you end up taking these tiny steps early on, and then the steps get bigger and bigger. So one of the ways we can fix this is we can divide mk by 1 minus beta 1 to the power k. Right? So this means that on the first step, m1 will be 1 minus beta 1 times the gradient, and when we divide it by 1 minus beta 1, you just get back exactly the gradient. So why? Well, because initially m0 and v0 will be 0, so early on these values will be small, and this correction kind of blows them up a little bit once k is small. Now notice that beta 1 is raised to the power k, so once you've taken many steps, let's say you've taken 1,000,000 steps, beta 1 to the power k will be almost 0, so 1 minus that will just be 1. So then m hat will be very similar to m. And we do the same thing to v hat. Okay, so we have this little correction that just speeds things up a little bit in the early stages of optimization. And then our update, theta k plus 1, is just theta k minus our learning rate alpha times m hat divided by the square root of v hat, just like an RMSProp, only we have this little epsilon, and this epsilon is just to prevent division by 0. So if v hat gets to be really tiny, we just add this little epsilon to avoid division by 0. That's all. A good choice of epsilon is 10 to the negative 8th power, so it's a really tiny number. All right, if you want to use Adam in practice, good default settings for many machine learning problems are to set alpha to 0.001, and to set beta 1 to 0.9, and beta 2 to 0.999. Why is beta 2 bigger than beta 1? Well, beta 1 is basically like the momentum term. Beta 2 is just estimating the magnitude. The magnitude doesn't tend to change as fast as the direction, so that's why we can use a larger value of beta for the magnitude, but we need to use a smaller one for the momentum because the direction can change a lot, and we don't want to average together really, really different directions too much.